And I will consent. Yes. Okay. Yes. Thanks for the invitation to speak. So, right, the title is K-theoretic sheaf-counting invariants of Quot schemes on C4. So, and this is joint work in progress with Martijn Kool. And there won't be any derived categories appearing in this talk. So, in that sense, it's a misfit for the derived seminar, although there will be there'll certainly be complexes of coherent sheaves. So I count that as sort of, yeah, that gives me permission for this to use this topic. And I realized in writing this talk that there's already a large amount of sort of technical sort of, well, seemingly unavoidable technical detail here, and doing Quot schemes is one detail too far. So really, for the purposes of this talk, we will be doing the case of Hilbert schemes rather than Quot schemes, but the general result has you can also extend it to Quot schemes. So the topic of the talk is to basically explain a computation of the K-theoretic sheaf-counting invariants of the title, and this computation is basically a proof of a conjectural formula for the generating function of these invariants. But so the main, the first point we want to get to is explain what they are. And I think it's useful to basically start by setting 4 equal to 3 and to talk about the case of these invariants for C3, because the whole story is formally very analogous to the 3-dimensional case, and it's very yeah, I don't know, and that case is somehow simpler and more well known, so I want to sort of set that up and recall that. So you have m equal to let's set m equal to the Hilbert scheme of n points on C3, and we're after in that case the sheaf-counting invariants are the that we're after are the K-theoretic dt invariants. So a key part of the geometric setup here is that there's a torus, which is c star to cubed acting on m in the obvious way, and M has a perfect obstruction theory, or perhaps to make it fully explicit, M has a 2-term perfect obstruction theory, and from, well, the fact that it has a perfect obstruction theory implies that we can define its virtual fundamental class in H0 of the equivariant homology of M. So that would give you the sort of the original DT invariant, or the cohomological DT invariant, or whatever you want to call it. The thing we're interested in today is the K-theoretic version of that. So there's this over M, which is called the virtual structure sheaf. And despite its name, it's not a sheaf at all. It's actually a K-theory class living in the T-equivariant K-theory of M. So it's some formal difference of T-equivariant coherent sheaves on M. And so the main so what you might call the K-theoretic DT invariant here is to take the integral of this in some sense, or I mean, what that means in K-theory is you you want to compute the Euler characteristic of this K-theory class. Okay, so this is now the main guy you want to compute, or this is at least, I mean, there are different versions of the DP invariant, but this is one guy which you would want to compute. Okay, so first of all, you should note that this doesn't make sense on the face of it. So note that M sorry, note that M is non-compact. So you're not allowed to apply this chi operation taking alternating sums of HIs. Well, at least it's not obvious you're allowed to do that. But in this case, the fixed point locus is compact, which means that really you are allowed to interpret this thing. I give meaning to this thing by saying it's defined by localization. So it's defined by localizing to the localizing with respect to the T action. So that is some general recipe which I won't go into, but the upshot is this thing produces. So this thing, if you define it by localization, you end up with something living in the equivariant K-theory of a point suitably localized, which has an explicit description as the ring of rational functions in T1 and T2 and T3. So here these Ti's are the coordinates of the torus T. So I should say this is the first time I'm giving a talk on this. So interruptions where you point out where things are unclear are very welcome. So right. So we can define this thing, and the output is a rational function in 3 variables. And in fact, we can do more than that. We can give an explicit, this localization can be made. So the localization is in general just some abstract way of defining this chi operation when you have a compact fixed point locus. In this case, we can be extremely explicit about what this localization does. So in order to explain that, let me just first remind you what MT looks like here. So MT, so the fixed points in the Hilbert scheme, that's the set of monomial ideals. So for a subscheme of C3 to be fixed under all rescaling of the parameters, it's the same thing as saying its ideal is generated by monomials. And these guys are in bijection with the plane partitions. It's called the plane partitions.
I have a question, Jørgen.
Thanks. Yes.
Is that your daughter we can hear?
You can hear her. Yeah, I was wondering. Yes.
Oh, okay.
She's
cool. It's nice.
Yes. They are squeals of enthusiasm, I think, not distress.
Of course.
Yes. Yes. Yeah. I don't know if there's a filter for removing that kind of noise. Anyway, these are in these are in bijection with plane partitions. So plane partitions are they are subsets subsets of this positive orthant lattice, satisfying. We want them to have size equal to n, and we want them to satisfy the condition that the complement is closed under adding on things in a positive orthant. Of course, this is the formal way to say it, and then really you should picture this as a set of boxes stacked at lattice points, stacked neatly into the corner of a room, and this is easy to draw, but it's beyond me. So that's just that's the picture you have in mind. So those label the fixed points, and I'm not going to use that much. It's just to make it clear that these are completely explicit, and the fixed point locus here is a set of isolated points. Okay, so now so we know exactly what the fixed point locus is. Okay, so what do we now do when we try and apply localization? We have the virtual localization formula. So there are various versions of this. But so this version is Fontanini and Kapranov. Which says if you want to evaluate in this case what you're doing is you're summing over fixed points with a specific contribution. And recall here, so a fixed point, this is the Hilbert scheme. So a fixed point is by definition a closed subscheme of C3, and so we can define it by writing down the following expression. Okay, I should, there's some notation to explain here. So first of all, when I write this, I mean, it's perhaps somewhat poor notation, but I've chosen it, so I have to stick to it. I mean the alternating sum of the ith wedge powers of what's inside here. And then these guys, so the things inside of this wedge bullet symbol, they are T representations, and I identify. So you identify T representations with characters. So again, these are, I mean, these correspond to polynomials in the variables Ti, and then this fraction gives you some. So in that sense, this fraction is a rational function. And when you try and work with this, and actually you can try and compute these things explicitly, all of these things, the x2 and the x1 are completely explicitly determined in terms of the combinatorics of the plane partitions. So if you have a powerful enough computer, you can compute this sum easily. It's all sort of explicitly known or knowable, so the computing this chi is in principle solved once you have this formula.
But it seems like an infinite sum of those rational functions.
It's not an infinite sum, and this is I was worried about this being an unclear point, so I've sort of fixed I've fixed an n since the beginning of the talk here, so it's really. Does that clear it up? So you're looking at fixed points in sort of inside of a specific Hilbert scheme, and the fixed point locus is this thing is a finite set. So I should have
Okay, yeah, thanks.
yeah. So it's really we're fixing a single n, and that's the m we look at for now, and eventually we'll stick them all together in a generating function. But for now, it's just a single n. Right. Okay. So this is somehow this gives you one approach to what this invariant is and how to compute it. There's another more global, more geometric way of looking at this thing. So when I introduced this virtual structure sheet to you, I just said there's a perfect obstruction theory. From that, there's a general recipe. Space with a perfect obstruction theory produces a virtual structure sheet. In this specific situation, this Hilb NC3 is somehow the simplest possible moduli space of sheaves on a Calabi-Yau threefold. So in this particular setting, there's a very explicit model also for what the virtual structure sheet is, which is technically useful. So this comes about because you can see M as a critical locus. So I know the goal now is to sort of tell you explicitly what over is in a way which is useful. So there's a general fact that the reason why Donaldson-Thomas various flavors of Donaldson-Thomas theory work so well in the Calabi-Yau 3 case is because moduli of sheaves on a Calabi-Yau 3 moduli of objects in a Calabi-Yau 3 category are locally they locally look like the critical locus of some function on a smooth variety. And for the case of Hilb, N, this is even true globally, so that sits inside NC Hilb N, which is I call it well, I don't call it, I mean, everyone calls it this, non-commutative Hilbert scheme, which parameterizes surjections from this polynomial ring in n non-commuting variables. So here n is some module over left module over this ring, and we set the dimension of n to be equal to small n. So if you wrote down this thing with the polynomial ring in commuting variables, that would be the definition of the Hilbert scheme here. The variables don't commute, so you get the definition of the non-commutative Hilbert scheme. Okay, so this is kind of it's an easy fact that this is actually a smooth scheme, and you define a function on it by saying this function evaluated at a surjection like this takes the value trace of x1. Okay, so here this thing, I consider this to be an element of the endomorphism ring of, or the endomorphism space of n. Okay, and with this function, you have the fact is that Hilbert C3 is the critical locus of W, by definition, the vanishing locus of this one form. Right. Okay. So this this buys you. I mean, this will buy you all sorts of good things. For us, the main point is it also gives you an explicit description of the virtual structure sheaf. Now you can set, let's call it just curly C. You can write down the complex, which is the cosrual complex associated with this section dW. So you have dW and then it stops it. Okay, so you have this complex, which is essentially, you know, if dW were transverse, and this would cut out Hilbert C3, and this would be quasi-isomorphic to the actual structure sheaf of Hilbert C3. As it is, it only gives you the virtual structure sheaf, and it does so by the following. Well, one way to phrase it is the following things, to say, well, the cohomology of this complex is a sheaf, well, or is a cohomologically graded sheaf supported on Hilbert C3, and then you take the virtual structure sheaf is actually now the class of this cohomology. Right. So this gives you both an explicit description of what. So it gives you an explicit description of what this K-theory class is, and I won't explain why that's important until much later, but just notice that this also gives you a lifting of this K-theory class to an actual sheaf. Like this cohomology, this object here is actually better than over, because this is an actual sheaf, and well, this more information, and which is useful in working with this thing, arguing with it.
So Jørgen,
yeah,
maybe it's worth saying at this point, since this is a derived category seminar,
yes,
that is not an element of the derived category. Like that can't be lifted in any natural way to be an element of the derived category. It is not the restriction of that complex. You know, I mean, it's a strange thing about K-theory. If something's supported on a locus, then it is the push forward of something from that locus.
Right.
Whereas that's not true in the derived category, right?
Right. So this thing. Okay. So if let's put some derived categories in here. So this thing is an element, or gives you an element in the derived category of NC Hilb, but it's not pushed forward from. It's not in the image.
I mean, not necessarily.
Well, okay, yeah. There's no good reason to think it would be. Yeah.
Right.
So it's a complex on the whole ambient space, but it doesn't. Yeah, you need to know about the ambient space somehow in order to define it. The trick we play here is somehow, well, there's an intermediate step between getting K-theory and having the full complex, which is taking cohomology. And for taking cohomology, you get something which actually lives on Hill, and doesn't need the ambient space anymore. So that's somehow, yeah.
So when you say supported, you mean scheme theoretically supported?
Scheme theoretically, yes.
Okay.
Yeah, exactly. So perhaps it's simpler to say this is a sheaf on Hilbert C3, like it lives on Hilbert C3. Okay, so I want to.
Sorry, Jørgen, can I ask one other question?
Yes, please.
At the beginning, you had two-term complexes.
Two-term, yes.
Which are obstruction.
Yes.
That seems to be longer than 2 terms.
Right. So this isn't the obstruction theory. So the two-term obstruction theory. This is an object. So that's right. So the obstruction theory is given by, well, roughly speaking, it's given by the fiber at each point is well, okay. The cohomologies of the obstruction theory are these spaces, these X groups, right? So the perfect obstruction theory is like more or less the virtual tangent bundle. Whereas this thing that I'm writing down here is the virtual structure sheaf.
Oh, so it doesn't, the virtual structure sheaf is not the class of the obstruction theory?
No.
Okay.
So obstruction theory is, I mean, if you want to do this like fully DG derived or whatever, the obstruction theory is the well, cotangent complex in the derived sense, and the structure sheaf is a structure sheaf. I mean, that's making that precise is icky, but they're really distinct objects. Okay, so I want to state how to compute these now. So this is yeah. So put a formula up for computing this. So we now okay. So I won't. Well, I can't. I don't know of a sort of a priori justification for doing this, but it turns out to be useful to, instead of taking the virtual structure sheaf, take the symmetrized. So this is the symmetrized virtual structure sheaf. Or if, I mean, a more usual way to write this is to tensor with square root of the virtual canonical bundle, but in this case, it really is tensoring with K and C Hilb. So this is just okay. I've defined a new class for you now. I'm introducing some notation in order to state a result. So I let as a general notation, I use square brackets to mean square brackets of eventually some polynomial to mean alpha to the power half minus alpha to the power minus 1/2, which will simplify the expressions I'm about to write. And I write, so if you have some function, or you should think of it as a formal power series, or it could be also perhaps a rational function. If you have some function in R variables, we write x with a capital E to be the exponential of the following expression. Okay, so this is the plathistic exponential. And roughly speaking, I mean, this corresponds roughly speaking to the operation. I mean, if your f is the character of some representation, then this taking the plathistic exponential is taking the direct sum of all the symmetric powers. This is the sort of the I don't know, polynomial level version of that operation on representation, so whatever. So the point of that is now you can okay, once you have this, you can write down the computation. Of invariants. So this is the theorem due to Konkov, conjectured by Nekrasov. Which is the generating function of all of these is expressed as the statistic exponential of something surprisingly simple. That's the way I think of it anyway. That's the way I remember it, and I have to look it up every time I'm supposed to really see what it is. And it won't, I mean, please don't pay too much attention because it won't really be important exactly what this is, but it's this factor, and then you take anyway, okay, yes, that's that is the theorem. Okay, so so hopefully it's at least clear what the theorem is. It's that a sort of qualitatively speaking, you have K-theoretic invariants given by the symmetrized virtual structure sheaf. You stick them all in a generating function, and this generating function turns out to be the statistic exponential of some simple rational function. And I mentioned this because so the reason I spend so much time on this is okay, the goal for the paper that we're doing is to do exactly the same thing one dimension up, do the same thing for C4, and not only is the result we'll find extremely similar to this result, the proof is also follows very much along the same lines and the same ideas. There's some new difficulties, but this turns out to sort of this theorem and its proof is the blueprint for what we do.
So, so previously you said we had 3 variables, right? T1, T2, T3. Why do we have 4 variables now?
Oh, this is just the there's an extra variable. So now I let the n vary, right? So now I'm adding this q, which is, I mean, the q doesn't live in a torus. The q is just keeping track of the various. So now we're sticking it all in a generator.
But do you have T4 like at the bottom, the denominator, like T1, T2, T3?
Did I? That's see, that's why. Yeah, as I said, it shouldn't be there. I can never remember how to write this thing. It'll show up later. It'll show up later. We're going to 4 dimensions now. Thanks. Yes. Okay. Sorry. So the Q wasn't the problem. The T4 was the problem. I understand. Okay. So let's now do the same thing for Hilbert C4. So in this case, we have a torus. We keep actually the 3-dimensional torus. And this thing naturally acts on Hilbert C4. So which 3-dimensional torus do we take? We take the one which preserves the volume form here. So, I mean, now that we say this, we really need in this case for T to act in a way so that Hilbert so that C4 is T equivariantly Calabi-Yau. And now the fixed points are just as easy as they were before. I mean, or similar to what they were before. So the fixed points are now solid partitions. meaning certain well-behaved, well, certain finite subsets of, well, you go one dimension up, and now you're stacking four-dimensional boxes in the corner of a four-dimensional room. And we would like to, well, we would like to have invariants first of all. That's so we want to do the same thing because we are somehow led to believe that we can do this, but we don't have a two-term perfect obstruction theory anymore. So before, the two-term perfect obstruction theory was x1 and x2, but now this the thing you write down will have an x3 in a picture, which will well, the obstruction theory is now, the natural obstruction theory is now, well, you might call it three-term perfect obstruction theory. So the general recipe for producing virtual structure sheaves doesn't work. It doesn't fit in this. So Hilbert C4 doesn't fit in this framework at all. So nevertheless, you know, there's been this has been in development for some time. You know, there's various versions of sheaf counting invariants for Calabi-Yau fourfolds, and I'll get to the one we use in a little while. But just before that, I want to say what. So the conjecture was stated even before we had the appropriate definition of this object, the virtual of the symmetrized virtual structure sheaf. So the ad hoc definition is to say, well, supposing you had a localization formula, then what would that localization formula be? And it turns out you can actually you could actually guess this before it was actually the output of a localization formula. So it has the following shape, or it is the following thing. So as before, you're considering x2, something to do with x2 in the numerator and something to do with x1 in the denominator, and so I need to explain the notation here. So first of all, the simplest thing to explain is I've added a hat on my wedge bullet, which just means take the old wedge bullet and tensor it with just, again, this is a sort of symmetrized wedge bullet. Anyway, it's not so important. The more subtle thing is I've introduced this thing which I call half x2. So what is this? Well, x2 has, in this case, has a non-degenerate quadratic form on it. Just by taking Serre duality, so x2 cross x2 goes to x4, which is isomorphic to C, and then, you know, Serre duality tells you this is non-degenerate. Then this thing is a maximal isotropic subspace. And you would rightly complain that there are more than one maximal isotropic subspace. This is some maximal isotropic subspace, and the claim, which is quite easy to verify, is that So different choices of. So I'm choosing some half x2 subspace, and different choices of half x2 give the same result for this class up to sign. Okay, so I wonder if I'm making this sound more complicated than it is. I mean, it's really when you sit down and work with this x2 is really an explicit in each case. If you're looking at a single fixed point, it's a Laurent polynomial in the parameters ti, and then you pick half of the monomials, and the claim is that you can sort of, there's some choice in which half of the monomials you pick, and then the choice only matters up to a sign. So there's a plus minus ambiguity here. So these, we're summing over all the fixed points. Okay, so this isn't really a definition at all, right? We've left lots of ambiguity here. So there's, and I mean, the number of fixed points is pretty huge. So the right-hand side is horribly undefined. So nevertheless, there was a conjecture. I mean, one conjecture that this comes from a sensible global theory, which would determine the signs, and then that would give you the right definition of the invariant. So the theorem that we prove, which is a conjecture by Nekrasov, is that for the right choice of signs, again, for the right choice of signs, you actually get a very nice formula. So the sum so now I'm forced to modify this a little. I won't explain much about why, but this is just part of the package. This thing is written as a platistic exponential, where you have t1, t2. You have, again, a rational function looking very similar to the one you had in the threefold case. And now you have a y term here and a okay, so to explain, so y here is just a formal variable, so sort of it's just a bookkeeping, so it's just a bookkeeping device, really. And ON is the topological bundle. Right. So this was a conjecture. So the result here is essentially sort of two things. We're pinning down the signs, and we're showing that once you've pinned down the signs, actually this localization formula, summing over all solid partitions with a specified weights of coming from half x2 spaces and so on, actually simplify to, or actually they sum up to this concrete thing. So, and as I said at the very start, this also has a version for Quot schemes, which was conjectured by Nekrasov and Piazzalunga, and we also proved that thing for Quot schemes. So I want to say, so this, I'm close to the nearing the. There's like 15 minutes left of my talk. Giving you the result, let me say something about why we're able to do this now. And the main point is I've been sort of stating this in the sort of chronological, in the sort of the order in which things were conjectured and described. So logically speaking now, we don't really need this ad hoc definition. So logically speaking, we now have a definition of what this O hat ver is, and this changes from like a definition to a theorem. And let me get to what changed as the work of Owen Thomas last year. So this, so they define well, both cohomological and K-theoretic sheaf-counting invariants for Calabi-Yau fourfolds. So this is not, I mean, this is in some sense, well, in a direct sense, in a literal sense, related to Borisov and Joyce's works. So Borisov and Joyce have defined these things in some setting at the cohomological level. There's also work by Kool and Long. So those previous works are more sort of differential geometric or even derived differential geometric, whereas Owen Thomas work in algebraic geometry, which is helpful for us. They also, I mean, they also do the K-theoretic invariants, which weren't there previously, and they also treat, this also works T equivariantly with a, and they prove we now have a localization formula. So O and T prove a localization formula. So so I want to say, okay, so how does this work concretely? So this runs extremely. This runs the story of Hilbert C4 is extremely parallel to Hilbert and C3, and we make strong use of the what you might call the standard model for moduli of sheaves on a CY4. So, so a moduli space of sheaves on a Calabi-Yau 3 is locally looks like a critical locus. A moduli of sheaves on a Calabi-Yau 4 locally also has a simple description or a sort of standard shape. So this is, so the M that you care about, you should think of as locally contained in some locally contained in some A, where A is a smooth ambient space. So the package, the data continues by saying you have a Q as an SON bundle on A, and there exists a section of Q, which is isotropic, and then M is cut out by this isotropic section. So previously, so in the Calabi-Yau 3 case, M is cut out by a one form, by an exact one form. In this case, M is cut out by an isotropic section of an SON bundle. Okay, so given, from the standard model, if you're given a standard model, OT produces a virtual structure sheaf, or a symmetrized virtual structure sheaf. And you can have a torus acting in there as well. Okay, so the observation now is the natural thing to ask, and it's quite simple to find the answer, is that actually Hilbert of C4 being the simplest modular space of sheaves on a Calabi-Yau 4, this sits inside NC Hilb and C4. So this fits in the standard model. So you can write down a completely explicit, completely explicit vector bundle Q, some SO, well, I won't use N, but some number bundle on NC Hilb, and a completely, very simply, simple to write down some section of Q which is isotropic, and then the Hilbert scheme is the vanishing locus of S. So it's really this is globally of the form that you have that somehow moduli of sheaves on the Calabi-Yau 4 is locally. Okay, so so once we have okay, so once we have this, once we can write down this local model, what do we get out of that? Well, we get out so consequences now. If you now apply the OT localization formula, I mean that that gives you back the ad hoc, the previous sort of ad hoc definition description for. So that turns now into a theorem, but not only that, so this is so the localization formula here is. I mean, it is a formula, so it's sort of, it doesn't leave anything ambiguous. So we also sort of specify with specific signs at each, specify the sign at each fixed point. And not only, I mean, this is so previously I left the sort of the signs completely sort of out there. You just sort of pick whichever ones you choose. Now that we have a global description of the object, it's kind of, it formally follows that the signs are determined. But we, more than that, the signs are not only determined, but we can explicitly describe them in terms of the shape of this, the plane partition of each, in terms of the shape of this solid partition, sorry, corresponding to the fixed point. So these signs are explicitly determined, which is, if you're looking at this from the outside, it's of course computing a sign is sounds very unexciting, but if you've been trying to do it for a long time, then it's this is a major win. So this is one.
So can I ask? I mean, does this mean you're also choosing these 1/2 x2 subspaces, or do you not need that?
You don't, and you so what you need to do is to choose. Well, these 1/2 x2 subspaces come in sort of they split up into 2 sets. So in order to apply the formula, you only need. I mean, it's really sort of just a mod 2 choice. This 1/2 x2. You don't need to specify exactly which subspace. Although you can, but that would be somehow arbitrary. Yeah. Yeah. So there's no preferred 1/2 x2 subspace, but there's a preferred I don't know, equivalence class of them, giving you the same sign. Right, and the second thing I want to, the final thing, the final ingredient in this, which is useful, which comes out of having this explicit local model, is we can actually do the same thing that we could do for the threefold case, which is so this. So this object that we wanted to integrate. So again, I have to now, in order to be honest, I have to put this complicated extra tensor factor in here. This thing, which a priori only lives in the K-theory of Hill, can now be refined. This can be refined to a sheaf, and this is now going to sort of tell you what the sheaf refinement of this OT virtual structure or synchronous virtual structure sheaf is in the local model. So and as this will be writing down a complex, and so in the standard model, where we have an M sitting inside an ambient space A, and we have Q and SO bundle on A, we assume, let's make this model even better, even simpler. We assume that Q is of the form L plus L dual, where L is some maximal isotropic subbundle. Okay, so this is a particularly simple kind of quadratic, particularly simple kind of SO bundle. So we have the section of Q, and we say S is equal to, I mean, it splits up where Sn is a section of the bundle L, and S2 is a section of the bundle L dual, and then you can write down the following complex, or it's kind of, yeah, the following complex. Start out with O, and we want to have L, and then we want to have a differential, which comes from, where do you find a differential? Well, we're pairing with is 2. And you take wedge 2 L, and then this is again. So it's kind of wedging with S2, but let's not do that. So you take the Koszul complex associated with S2, and then you have maps going the other. You have differentials going the other way as well. So here you're really wedging with S1. So and so on. So here you have a differential. So this is this. Okay, so this isn't a complex in the usual sense, right? Because the differential doesn't increase the degree by 1, but this is a Z mod 2 graded complex. And if you're familiar with matrix factorizations, there's matrix factorizations lurking in the background here. But this is, I mean, this can also simply be described as a Z mod 2 graded complex. And you have exactly the same thing happening as before, that the cohomology of this thing, which is now splits into just even and odd parts, but this is a sheaf. Yeah, this is a sheaf supported on M, and the symmetrized virtual structure sheaf is the class of this sheaf tensored with the square root of the determinant of L. Sorry. So I think I'm running out of time now, but the point of all of this is now you can. So the point of all of this is now you can say we can set Fi to be a sheaf, to be this sheaf refining the class we had before. And well, okay, that's I think that would be too much to go into, but having these sheaves, so this is a sheaf on Hill by C4, and having these sheaves on Hill by C4 is really what sort of allows, so you can relate these sheaves for various I, which gives you a lot of geometric input in order to constrain the whole generating function that you're interested in. And that's the first step in the proof, and then you have to really look specifically at what these localization terms is to get all the way there. But this is at least the geometric side of the story, is refining these two sheaves and understanding how they connect for various Hill by, and that part of the story is directly a direct generalization of what happens in the Hellbent C3 case. Anyway, I think I should stop here.
Okay, thank you. Any questions?
Can I ask what this non-commutative Hilbert schemes? Why are those smooth? How does this work?
How does this work? So they admit. So if we look at what they are, let me see. So here's the definition of them, right? So you have there's cyclic modules. Sorry, there are modules over this non-commutative polynomial ring, along with a map from this non-commutative polynomial ring, which generate them. So what this means is you can write down an explicit GIT presentation for them. So you can write down, say these are, in this case, it would be this has an explicit GIT presentation. So it's so I should it's right. So that is how you see. That's how I would say I see that they're smooth. They're you can write them as a GIT quotient of something smooth, and you can check that you're sort of the GIT. It's really I don't know, a geometric GIT quotient, or there are no stabilizers or anything like that. So that's the.
So this is for any n, right? So not just 3 and 4, but for all of all.
Yes. Okay. Completely general.
Okay.
Right. Another sort of they're in the corner of like I mean, these are, you can also see them as moduli spaces of representations of a certain quiver, stable representations of a certain quiver, and then for quiver representations there's also, well, basically for the same reason things are smooth.
Can you say something more about your standard model for the HIP NC4 case? I mean, you said it's easy to write down, so maybe
Yes,
can you just write it down?
I was saving on time. I can try and write. I can write it down. It's easy. So and now people are free to log off, I think. So Hilband sits inside NC Hilband, and we want to produce an SO bundle on NC Hilband, and this should be. We just think of this as tensor, or rather, I should say. So we're in NC Hilb, right? So a point is a surjection from this polynomial ring to some module. And I claim the fiber should be, the fiber at a given surjection should be wedge 2C4 tensor the endomorphisms of the vector space underlying that module. So we need to produce a quadratic form to turn this into an SO bundle, and that is taking seeing this thing, gives you this thing, which lives in wedge 4C4 tensor C equals C. So that's that's how you produce a quadratic form. And then the section at the point N should be the sum over EI. So this commutator is something living in the endomorphisms of N, and here the EI are a basis of C4, so we sum over I j equal 1 to 4, and so then this thing lives in to C4. Okay, so that's it. That's enough to that's the description of what the standard model description of Hilden inside NC Hilden C4 is. So then you can check. Okay, so when does S vanish? S vanishes at a module if and only if all these commutators vanish. So it's really encoding. S vanishing is the same thing as commutators in the action of this module vanishes, which means that the module is in the actual commutative Hilbert scheme and not the non-commutative one.
So can you extend that to more general quivers? Somehow can you formalize what goes into it and then?
So it's an interesting question, right? So and certainly you can try and write down models which don't come from a four-dimensional geometric object. Just sort of, so in the 3D case, you can take a quiver and a potential in the quiver, and you would generate things which are critical loci. Here you might start with a quiver and put some extra data on it to produce something in the four-dimensional standard model. So the only general thing that I can think of is if you start with a quiver and a function on it, so something which is CY3, a quiver with potential, you can add on a direction to produce a four-dimensional thing. You sort of add on a trivial direction. So a generalization of there's a way of passing from the 3-loop quiver to a 4-loop quiver, which is exactly this passage from Hilbert C3 to Hilbert C4. And similarly, you can take any quiver and sort of add on loops at all the vertices to produce something which behaves like the four-dimensional standard model. And those, you would think that the methods used here would also somehow apply to relate the original quiver to the new sort of four-dimensional thing. But that's the only general thing I know.
Can I ask something completely different? I mean,
Yes.
Does your result shed any light on any compact situations?
It's yeah. The only honest answer is it's unclear to me. It might, but we haven't thought about that at all. So yeah, I basically I don't know if there are general ways of passing between the compact cases and this local case, and yeah. The short answer is you would hope so, but I literally don't know.
Okay. Any other questions? So if not, then let me stop the recording and